This is the inside of a boiler furnace. Here, water in the tubes lining the walls of the furnace absorbs heat from burning fuel. The water is boiled, producing steam that drives a turbine and also provides heat for other systems in the plant. Water circulation in a boiler is necessary for two reasons. First, it provides a constant supply of water to be turned into steam. And secondly, it carries the intense heat of the boiler furnace away from the boiler tubes, preventing the overheating and rupturing of the tubes. In a typical drum-type boiler, the water flow path includes an economizer, the boiler drum, downcomers, headers, and the boiler tubes. The water that is supplied to a boiler is called feed water. The first component that the feed water passes through is the economizer. The economizer uses heat from combustion gases that would otherwise flow out of the stack to heat the feed water. Heating the feed water means that less fuel has to be burned in the furnace to convert the water into steam. In this boiler, the heated feed water flows from the economizer and enters the bottom part of the boiler drum through the feed water inlet. The water continually circulates within the boiler through the downcomers, the lower headers, and the boiler tubes. A boiler typically has 2 or more downcomers and 2 or more headers. However, for clarity, this illustration shows only one of each. The lower headers supply water to the bottoms of the boiler tubes. The boiler tubes, which line the inside walls of the boiler furnace, are commonly called water walls. The water walls are exposed to the heat produced by burning fuel. As water flows up through the water walls, heat turns some of the water into steam. The mixture of water and steam rises until it enters the boiler drum, where it's separated into water and steam. The steam rises to the top of the drum, and the water remains in the bottom. The water is then available to recirculate through the boiler. The flow of water through some boilers occurs by means of natural circulation. The key to understanding natural circulation is the fact that cold water is heavier or denser than hot water or steam. In a boiler, the mixture of water and steam in the water walls is hotter than the water flowing from the drum through the downcomers. This is because the water walls are heated by the burning fuel in the boiler furnace. As the mixture of water and steam rises, cooler water from the downcomers flows into the lower headers and then into the water walls. The cooler water is also heated and rises, creating a self-sustaining flow through the water side of the boiler. Natural circulation of water in a boiler is affected by two factors. They are the amount of heat produced in the boiler furnace and the pressure at which the boiler operates. For example, raising the temperature in the boiler furnace increases natural water circulation because it results in a greater temperature difference between the water walls and the downcomers. Increasing the second factor, pressure, has a negative effect on natural circulation because as pressure increases, the density difference between water and steam decreases. In some boilers, boiler water circulation pumps are used to increase circulation. Circulation that uses pumps is often referred to as controlled circulation. The pumps force the cooler water from the drum through the downcomers, into the lower headers, and up through the water walls. The increase in flow over natural circulation provided by the pumps allows more heat to be absorbed by the water. As a result, controlled circulation boilers can produce more steam for a given size boiler. A boiler drum has two main functions. It receives heated feed water to make up for water that's converted to steam and flows out of the boiler. It also collects the steam that's produced in the water walls. This is a simplified cutaway view of a typical boiler drum. The bottom part of the drum contains water to be circulated back through the boiler. The top part of the drum is used to collect steam. Heated feed water is fed into the drum through a distribution pipe. The drum is usually kept about half full of water. In this example, the mixture of water and steam that returns to the drum from the water walls is directed against baffles called drum shrouds that run the length of the drum. The shrouds direct the mixture of water and steam into moisture separators, which are located at the top of the shrouds. The moisture separators separate the water from the steam. The water falls into the lower part of the drum, where it mixes with the feed water. The steam rises into the upper part of the drum. The steam could still have some water mixed in with it. So in this example, it is sent through dryers, which are located in the top of the drum. The dryers remove as much water as possible before the steam leaves the drum. This is important because water that flows out of the drum with the steam could damage downstream components. The steam is discharged from the drum through steam outlet pipes. Between the time that steam leaves the boiler drum and the time that it enters the condenser, it is acted on by components in the steam flow path. To understand what these components do, you need a working knowledge of three basic concepts that are associated with the production and use of steam. They are boiling, saturation temperature, and superheat. Boiling is the process of converting water into steam. For any given pressure, there is a corresponding temperature at which water boils. The temperature at which water will boil at a given pressure is known as its saturation temperature. As pressure increases, saturation temperature also increases. For example, at sea level, atmospheric pressure is 14.7 pounds per square inch. At that pressure, the saturation temperature of water is 212 degrees Fahrenheit. At a pressure of 1,000 pounds per square inch, the saturation temperature of water rises to 545 degrees Fahrenheit. When boiling occurs, as in this water wall, both water and steam are present and at saturation temperature. No matter how much heat is added to the boiler furnace, the temperature in the water walls will never rise above the saturation temperature as long as water is present. However, after all of the water has been removed from the steam, the temperature of the steam can be raised above the saturation temperature. Steam that has been heated above the saturation temperature is called superheated steam. Superheated steam is desirable because higher temperature steam can do more work in the turbine. Additional work from the same amount of steam production makes for a more efficient generating unit. The steam in the drum of a typical drum-type boiler is at its saturation temperature. As the steam leaves this drum, it passes through moisture separators and dryers, which remove water from the steam and thus prepare the steam for superheating. Once the water is removed, the steam is sent to separate sets of boiler tubes called superheaters, where it is heated above its saturation temperature. The superheaters are positioned so that they are exposed to heat from combustion in the boiler furnace or from hot combustion gases. The superheater tubes absorb the heat and transfer it to the steam passing through them. There are several ways of classifying superheaters. For example, a superheater may be classified as a radiant superheater or a convection superheater. A radiant superheater is in a direct line of sight with the flames in the boiler furnace, and it receives most of its heat by radiation from the flames. A superheater may also be classified as a primary superheater or a secondary superheater. A primary superheater is a superheater that the steam passes through first. It's usually a convection superheater, and it's generally in a cooler location than the secondary superheater. The primary superheater is designed to raise the temperature of steam from its saturation temperature to a specific temperature range. The secondary superheater raises the temperature of the steam again. The secondary superheater is usually located closer to the boiler furnace so that it's exposed to higher temperatures. The secondary superheater may be either a convection superheater or, as in this case, a radiant superheater. This boiler has an attemperator, or desuperheater, located between the primary and secondary superheaters. The desuperheater keeps the steam from becoming so hot that it damages the superheater tubes. If the steam gets too hot, the desuperheater sprays water into the steam flow. This water immediately flashes to steam and mixes with the steam that's already there. The result is a decrease in the temperature of the superheated steam. From the secondary superheater, the steam goes to the high pressure or HP section of the turbine. As the steam flows through the HP section, it gives up a lot of its energy and its temperature and pressure drop. Before it moves on to the other sections of the turbine, the steam returns to the boiler, where its temperature is increased as it flows through one or more reheaters. Reheaters are very similar to superheaters. They use heat from the boiler furnace or from hot combustion gases to raise the temperature of the steam. For example, this boiler has a primary reheater that the steam enters first as it comes from the high pressure section of the turbine. After the steam flows through the primary reheater, it moves on to a secondary reheater. And a temperator located at the beginning of the secondary reheater is used to control the final temperature of the superheated steam leaving the secondary reheater. The temperator sprays water into the steam flow if the steam gets too hot. The secondary reheater in this example can also be classified as a radiant reheater because it's located in a line of sight with the boiler flames and receives most of its heat by radiation from the flames. The primary reheater is located farther from the flame, and it receives most of its heat by convection from the hot combustion gases, so it can be classified as a convection reheater. After it's reheated, the steam in this steam flow path flows to the intermediate pressure, or IP section of the turbine, and then through the low pressure, or LP section. From the low pressure section, the spent steam flows into the condenser. Inside the condenser, the steam flows over tubes that contain cooling water. The water in the tubes absorbs heat from the steam, and the steam condenses back into water. The water is collected in the bottom of the condenser and pumped back to the boiler to begin the cycle again. At any given pressure, there is a corresponding temperature at which water will boil. This temperature is called the saturation temperature. For example, at standard atmospheric pressure, which is 14.7 psi, the saturation temperature of water is 212 degrees Fahrenheit. When pressure increases, as it does in this boiler, the saturation temperature also increases. At 1000 psi, the saturation temperature of water is 545 degrees Fahrenheit. When the saturation temperatures for water at different pressures are plotted on a temperature versus pressure chart, a line is formed showing the relationship between saturation temperature and pressure. However, this relationship between temperature and pressure only holds true up to a certain point. That point, which is called the critical point, is 705 degrees Fahrenheit and 3,206 psi. At or above the critical point, the densities of water and steam are the same. In other words, there is no distinguishable difference between water and steam. When a boiler's temperature and pressure are above the critical point, all of the heat produced in the boiler can go toward raising the temperature of the steam. But boilers that operate below the critical point always have to use some of their heat to convert water into steam. So all boilers that operate below the critical point have a built-in inefficiency. Boilers that operate below the critical point are called subcritical boilers, while boilers that operate above the critical point are called supercritical boilers. A once-through boiler gets its name from the fact that water is pumped through it only once. It's not recirculated. Many once-through boilers are operated at supercritical conditions. In a typical supercritical once-through boiler, boiler feed pumps force the feed water through a header at the bottom of the furnace and up through the water walls. As the water flows through the water walls, its temperature increases. The water in the water walls is already under a very high pressure, typically around 3,500 psi. That's well above critical point pressure. When the temperature rises above the critical point temperature, water becomes indistinguishable from steam. The section of the water walls where this happens is called the transition zone. There is no need for a drum, moisture separators, dryers, or a recirculation system, because once the flow is passed through the transition zone, there is no water left to recirculate. The steam that leaves the transition zone moves on to the components in the boiler's steam flow path. The components in the steam flow path are generally the same for supercritical boilers and subcritical boilers. The main advantage of a supercritical once-through boiler is that it operates more efficiently than a subcritical boiler that has to recirculate water in the process of producing steam. A supercritical once-through boiler requires less fuel than a drum-type boiler of the same size to produce the same amount of steam. That makes a supercritical boiler less expensive to operate. However, while supercritical once-through boilers tend to be cheaper to operate, they're more expensive to build and maintain since special materials are needed to withstand supercritical temperatures and pressures. As an operator, you'll be responsible for maintaining the correct steam pressure in your boiler. To do this, you need to know some of the factors that affect boiler steam pressure. In a drum-type boiler, steam pressure depends primarily on firing rate. Assuming the demand for steam doesn't change, you have to maintain a constant firing rate to maintain a constant pressure. If you reduce the firing rate in the boiler furnace, the boiler will produce less steam and steam pressure will decrease. If you increase the firing rate in the boiler furnace, more steam will be produced and steam pressure will increase. In a once-through boiler, the heat produced in the furnace has little effect on steam pressure. That's because the pressure in this type of boiler is controlled primarily by the boiler feed pumps. If the pressure produced by the boiler feed pumps is reduced, the steam pressure will decrease. If the pressure produced by the boiler feed pumps is increased, the steam pressure will increase. Lowering the firing rate in the furnace of a once-through boiler will only cause the temperature in the water walls to drop. Pressure is not significantly affected.